I'm Terry Adams, Golf 4 Charlie Hotel Delta, and early this year I gave a talk to the Appledorn District Amateur Radio Club up here in North Devon on the design of a compact 20-metre antenna. And this talk was also live streamed via YouTube. Today I want to talk about how a subsequent discrepancy in the design has been investigated and whether the findings have caused any change to the final design. So it seemed a good idea to start with a brief summary of that initial design. And here we have it, and as you can see, it's based upon a delta loop with a corner at the top and horizontal wire at the bottom, just 1 metre above ground, and as you see, it's fed very conveniently at a bottom lower corner. A delta loop at 20 metres would normally have a side length of about 7 metres, which is really too big, certainly for what I wanted, and as I'm trying to produce a compact antenna, I thought I'd investigate whether or not adding an inductor to the design would reduce it. And after some experimentation, as you can see, I finally settled on a 20 microhenry inductance to be fitted halfway along the sloping wire diametrically opposite the feed point. And this worked perfectly. As you can see, the final size of antenna when trimmed to resonance at 14.2 megahertz was around about 4.63 meters, which is obviously considerably shorter than the 7 meters. And the SWR was nigh on 1-to-1, and the radiation plot pretty well omnidirectional, I reckon to within an S point, and most of the radiation less than 45 degrees with the peak at less than 30. So really it seemed to fit all the requirements, and several have been built by local amateurs within the club, and they in turn have reported good SWR and performance, but the discrepancy is in terms of the overall size of the antenna. Originally I found that the size was considerably shorter than predicted, and at first I thought that was down to me, due to the circumstances of the antenna at my QTH, nearby objects, etc. But when other people began coming up with a similar conclusion, I realised that something was amiss, and I thought it needed looking into. Because I'm one of those annoying people that like things right. And so I started going back to Easy NEC, the Pro 2 Plus, which is a free version now, which I used to design the antenna, and I tried changing just about everything to see if I could get an output which size-wise resembled what was achieved in practice. And the only way that I could get anywhere near was if by some magical wand the inductance changed from 20 microhenries to nearer 26, even 27 microhenries. And I honestly couldn't see how on earth that could happen, but nonetheless I decided that it needed to be investigated practically, and at least this analysis had pointed the finger at the measurement of inductance. And so that's what I'm going to do in this talk. So we'll start by actually looking at the equipment that has been used to measure the inductance as the coils have been made. And this is a coil, and a big thank you to Mike G4CHD, who very kindly has made the coils in a far more professional way than I could ever do. And this is the test kit, which is made by Peak, and it's the Atlas LCR meter. And without any further ado, I'm just going to switch it on, and it takes a while to warm up. Then it analyzes whether it's an L, a C or an R that's connected, and will finally display. And we now appear to have a reading. You can either see it, but if I can try and raise that, and hopefully you can get a better view, I make that 20.1 microhenries, and if I give a click, it's reading 0.2 of an ohm. So I would say I'm well pleased that the coil appears to have an inductance within 0.1 of a microhenry of what it was designed to be. But that doesn't do anything to solve the discrepancy that we've got. And I suppose at this point I just happen to have a read of the manual. And I'm afraid one of those people that, you know, it's the last thing I look at, and really very remiss. So I had to look at the section on inductance measurement, and it states quite clearly that for inductances up to about 1 millihenry, which of course this falls into, the measurement frequency is 200 kilohertz. That's 0.2 of a megahertz. And this was a sort of mini light bulb moment, because, okay, it's 20.1 microhenries at 0.2 of a megahertz, but the big question mark is, what is it at 14.2 megahertz? And the only way I'm going to get to the bottom of that is actually to measure it at that frequency. Enter my trusty bit of kit, which you possibly will immediately recognise, and that is the Nano VNA. And I've got a lead here which ends in a pair of croc clips, and if I can just clip that onto the coil, which I've done now, and this is a lead which I purchased from Amazon. It's got a male SMA at this end, which is perfect for fitting onto this port, and croc clips, as you see, at the other end. As supplied, it was a bit too long, about half a metre, and again thanks to Mike PGA for just shortening it to this more manageable size, as you can see. And also, just about glimpse at the bottom here, the USB cable as supplied with the Nano VNA, which is connecting it to the computer that's running a bit of free software called Nano VNA Saver, which I can strongly recommend, and which I'm going to use in this talk. So I'm going to switch on the Nano VNA, and we'll see if we can immediately have a look at the program running on the computer, Saver. And here we have it. And the first thing I'm going to do is it's found the Nano VNA on COM3, and I'm going to connect to the device, and hopefully that's now been connected. The next thing I'm going to do is go into the calibration section, scroll down to loading a previously stored calibration, and this is it. I'll click on that, and I'll now get rid of this window. This is a previous calibration that was made using Nano VNA Saver, and the short, open and 50 ohm loads were connected at the ends of the croc clips, which then becomes the measurement plane, the calibration plane, and that's brilliant because that's exactly where the coil is connected. The next thing I'm going to do is change the sweep from starting at 50 kilohertz, which is okay, but I really only need it to go up to 40 megahertz. And in Saver, you can change the number of segments, and this is a way of decreasing the step. Here you can see it's nearly 400 kilohertz steps. By changing this now to 20, it's dropped it to 20 kilohertz steps. That's one of the most powerful aspects of this program. And to the right here you'll see there are two displays. The top one is the Smith chart and this bottom one is a plot of total impedance of the coil against a linear scale of frequency, which is going up to, well, here I think it's up to, and that will correct once we start sweeping. So if we start the sweep, and away we go, and as you can see down here now that has changed and it's up to 40 megahertz. But before it's actually gone too far, I'm going to stop this, and at the moment we've got three markers, a red, a green and a blue, and the middle green one, I'm going to change that from 50 to 200 kilohertz, and it gets rounded off because of the steps. And this now will enable us at marker 2 to read off what the inductance is and compare it with what we had with the LCR meter. And marker 3 I'm going to change to 14.2 megahertz, again rounded off pretty near 14.2, and we'll start it sweeping again. And also, just to be on the safe side, I ought to change that to a continuous sweep. And if we now do that, then at least this should keep sweeping, which it now will. Let it go through a couple of sweeps so that it can just average out, and then what I'm going to do is to have a look at this marker 2, the green marker, and as we've seen it's at 208 kilohertz, and that's on the Smith chart, and it's reading an inductance of 19.7 microhenries. And I'm pretty pleased with that because the LCR meter gave 20.1, which is a difference of what, 0.4 of a microhenry, which I think is what, 2% different. And I think that's pretty close enough to give confidence that the nano-VNA and the LCR meter are in agreement generally. But what we do want to look at is marker 3, and we'll see now that at 14.2 megahertz the inductance appears to have changed from 19.7, and it's now almost 25 microhenries. And this indeed was the light bulb moment, because that is in keeping with what I found when I was playing with Easy NEC, in that the only way I could get similar antenna lengths with Easy NEC was if the inductance wasn't 20 but somehow was nearer, as I say, 25, 26, something of that order. And this indeed has been borne out in practice. But how? How can the apparent inductance change? If we now look at this bottom display, and we appear to have a very predominant peak in impedance, and whenever I see something like that, immediately I think of a parallel LC circuit. And if we click on it very roughly, then the red marker is at 29 megahertz, round about the 30 megahertz region. And if we think back to the formula for a parallel tuned circuit, F is 1 over 2 pi, the square root of LC. We know F is 29 megahertz, 2 pi obviously. We know the L is 19.7, say, microhenries. It only leaves C unknown, and if you do the sums on the calculator, you come up with a figure of something like 2 picofarads. And indeed, that's just what's happened, that the coil in reality is an inductance in series with a very small resistance, but the whole lot is shunted by a parallel capacitance of around 2 picofarads. So what we now really need to do is to move into Easy NEC and just see whether by putting in these values that we've now established, that now Easy NEC will predict a similar size of the antenna to what's achieved in practice. This is going to need a change to obviously the load section, but before we do, there are also changes to the wires section, which, as invariably whenever you're developing anything, when you do the prototypes, you find that there are changes that need to be made. And a couple of changes. Number one was that the wire was used initially was quite thin. It was very good antenna wire from Sotobeams, and it worked perfectly. It was just that when you're constantly taking the antenna up, down, it tended to easily tangle, put it like that. And so got back to Sotobeams and purchased what they term the heavy duty PVC coated stranded antenna wire, which has worked out beautifully. And this means, of course, that the diameter of the conductor, which according to their specification is equivalent to something like 17 AWG, and the thickness of the insulation would need to be changed. And the second thing that was found was that with the telescopic glass fibre pole that was being used by myself, and indeed Mike PGA found the same, it just happened that when you opened the number of segments of the pole, the base of the antenna seemed to be happier sitting around about half a metre above ground, and that's what we've also decided would be a good thing to put into the formula. So let's turn straight away to Easy NEC, and here is the whole program with all its windows running. And first of all, we're going to have a look at the wires, and I'm not going to spend long on this. Very quickly, we've changed the wire diameter of the conductor, we've changed the thickness of the insulator, no change to the insulant because it's still PVC. And for wire 1, if you look carefully for the Z components, it's changed from 1 to 0.5. So that's taken care of that. If we now look at the wire, you still see that it's wire 2, 50% along. The resistance I've increased. I know we measured 0.2. I've just increased it to 0.4 just to be slightly on the safe side. The inductance you'll see is 18 microhenries, because obviously what we found is that whatever what we make the coil for in use at the higher frequency, it's going to be increased. So it was decided maybe to change the starting inductance, and by taking 2 turns off, so that instead of, I think it was a 22 turn coil originally, by dropping to a 20 turn coil, we ended up with an 18 microhenry coil. And the thought was that then at 14 megahertz it's going to be 20, 21, 22. I'm quite happy with that. It's better than it being up around about 25, 26, 27 microhenries. And then under the C column, the most important thing, we didn't have anything there before, but now of course we've got 2 picofarad. In the R frequency column, that I will put my hand up and say was incorrectly entered as 14.2 megahertz previously. What should be entered here is the frequency at which the resistance in the R column was measured. And as we measured 0.2 of an ohm at 200 kilohertz, 0.2 of a meg, that's what I put in there, 0.2 megahertz. And finally, the most important correction or change of all, and that is the config is changed from series to now trap, so that we have got its terminology in Easy NEC terms of meaning a LR circuit shunted by a capacitor. And you then run Easy NEC as we did before in talk 1, changing the size, etc., to bring the antenna to resonance. And finally, we arrive at this. As you can see, the base is now only half a metre above ground and the coil is 18 microhenries, and the size of the coil of the loop when resonant at 14.2 megahertz turns out to be round about 4.3, not 4.6 meters, a good 20-30 centimeters less, and very, very close. I personally found that mine was within a few centimeters of the 4.3. So at long last, we've actually got theory and practice tying up with each other, which makes me a happy bunny, shall we say. And of course, what matters is how this is going to perform. And if we look, the SWR still predicted to be almost 1-to-1 at 14.2 megs, and still a pretty omnidirectional antenna with most of its radiation below 45 degrees and predominantly around 30 degrees or less. And really, I would say that concludes the whole design process. I feel once arrived at a compact antenna, which I've tended to just nickname the compact ham delta, and it works pretty well as predicted, with a good low SWR, so you don't need an ATU, good low angle radiation, so that you can certainly work a good BDS. I mean, I think I have worked Asiatic Russia on SSB with 100 watts, which would be unheard of with my long wire that I was using before. And I know that Mike PGA on FD8 has worked VK, and when we looked at PSK Reporter, there was dots all over the place that he'd been heard. So I'm very, very pleased. I would say job done. And really at this point, all I can say is thank you very much indeed for listening. And I would just say have a go if you want to. The whole cost of the antenna is, well, £80 at the very, very most. Probably you've got quite a few of the bits and bobs anyway in your drawer. But if you want to have a go and you want any help, then don't hesitate to give us a shout. So with that, all I can say is sort of very best 73s, and many thanks indeed for watching.